So this is chapter 6 notes. We start with bonding. And the biggest deal that we have to know is the difference between a covalent bond and an ionic bond. And covalent bonds are also called molecular bonds. So covalent and molecular are the same words. So as an intro to this, it's important to understand the difference in the fact that this sharing of electrons. So if you are a co-owner or a co-worker, you're sharing something. So they are sharing electrons. And you can see that illustrated here. So a bond would be sharing these both electrons. So if you went over to someone else's house and you had some toys and someone else had some other toys, you could share them and both be able to play with both toys if you're sharing. Ionic bonds are a little different. Reminder, an ion is an atom with a charge. So when we're talking about ionic bonds, we're talking about things with charges. So it's an electrical attraction between large numbers of cations and anions. And we've already talked about this earlier in the year, but a cation, I will talk more about it, but has a positive charge and an anion has a negative charge. So opposites attract. So what actually ultimately happens in this is that one atom will give away an electron to another one. So atom with a spare electron, it says here, will give away its electron to an atom that needs an electron to become stable. And because of that, this will become a positive atom because it lost a negative, and this will be a negative atom because it gained a negative. So then I have a positive ion and a negative ion, and they're attracted to each other because of the opposite attraction. With that, we're going to learn this term called electronegativity, and it's kind of a big word. But what it means is when an atom pulls electrons from another atom in a bond. So if you are electronegative, you have this ability to pull electrons towards yourself. Okay, so there's 3 kinds of bonds, and there's a help sheet online that talks about this with Lewis structures and everything else. So I have all of them right here. And then there's values, see to the right here. These values are not having to be memorized. These values are just know how to use them. So I have 3 different types of bonds here. And I want to show you kind of the difference between them. If I have 2 atoms here and their electron clouds are kind of evenly shared, so the electrons are shared equally, then I consider that a nonpolar covalent bond. So covalent means to share, and nonpolar means that I don't really have differences in poles, so I don't have a really positive or negative end. And that's because the atoms are not really pulling the electrons harder from one to another. So they're equal pull, kind of like tug of war. Think of it as that. So the electronegativity difference is 0 to 0.4. So for example, if you come over here with the cursor, excuse me, and you look at carbon and hydrogen, 2.5 right here minus 2.1 is a difference of 0.4. So any carbon-hydrogen bond would fall in this range, would be nonpolar. As the same, like if you had oxygen-oxygen, 3.5 to 3.5 is 0 because you can't pull harder against yourself. The second one, what if you can share? You don't have to share equally, but what if you share? So what if this atom pulls some electrons from this one further to the left? Well, then they're not shared equally, but this one still has some electrons. So then we say that this atom, because it has more negatives, bigger cloud, has a little bit of a negative side. This has a little bit of a positive side. So we say they are sharing, so it's covalent, but there are differences in charge. So that's the definition of polar. So it's polar covalent, and that's our range of 0.5 to 1.7. So if we look at different kinds of atoms like that, we could take, just as an example, chlorine, and if it's bonded with, let's just say nickel, 3.0 minus 1.9, and you get 1.1. So that would fall in that range. Then we have the one that would be the greatest, and what this means is that this atom is so powerful and it can pull electrons so hard to itself that it rips all of the electrons from the other atom, and it's just kind of like a whoop, and it comes all over here, and this is very negative, this is very positive, and there's no sharing. So we call that an ionic bond. If you remember, an ionic bond means that there's a positive and a negative. There's no sharing. So that is some of the bonding that we have. Waiting for the next page. This is electrons revisited. And if you remember, some electrons, we talked about how to become stable. What needs to be stable? They all want to look like a noble gas. So if I want to look like a noble gas, I need to gain or lose electrons to get there. So if I look at this, here's 3 examples right here, and I've already filled these in. But if this is sodium right here, this is aluminum, and this is chlorine. I just picked 3 of them. If I fill this in, sodium, I'm just going to talk about 2 of them. Sodium is number 11. So I would have 1s2, 2s2, 2p6, 3s1. Why? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 electrons there. This is 13, so that's why there's 13. And I guess I'll talk about the last one. Chlorine, here's 17. Well, I have this box because what really matters is the outer electrons. The outer electrons have to look like argon or some other noble gas. The key is 8. They want to have 8, which we're going to learn in a second. So if I summarize this then, this is 3s1. This is 3s2, 3p1. This is 3s2, 3p5. It's all the outer electrons. Or if I can say just s1 or s2p1, or again s2p5. So the ultimate goal is those numbers right there. I have 1 electron in the outer energy level. I have 3 electrons in the outer energy level, or I have 7 electrons. So if you just look back up here, it's really 1, 2, skip over the transition metals, 3, 4, 5, 6, 7, 8, right? All the way through 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And that's what this definition is. Very important definition. Valence electrons, it's the number of electrons in the outermost energy level. We care about those the most. Anything else is just kind of filling up the space. So how do we show it then? This is how we show it. Think of an atom as having 4 sides, 1, 2, 3, 4. We're only going to show the number of dots that we have valence electrons. So sodium has 1 electron. So I'm going to put 1 dot. Aluminum has 3 electrons. So I'm going to do 1, 2, 3. I don't double them up. I try to spread them out. Skipping to chlorine for now, it had 7. So 1, 2, 3, 4, 5, 6, 7. Phosphorus makes sense to have 1, 2, 3, 4, 5. So phosphorus would have 1, 2, 3, 4, 5 valence electrons. And this is the beginning of Lewis dot structures. Hence the name Lewis dot, because there's dots. So you got to know this rule first. It's called the octet rule. Octet means 8. So we want to reach 8. Compounds tend to form so that each atom, by gaining, losing, or sharing, has 8 valence electrons. That's kind of the key thing. I think that's how it looked. There's one other rule. It's called a duet rule. So if an octet is 8, duet is 2. So hydrogen and helium can only get 2. The reason why it's in the first energy level. So it can only have a 1s, and 1s can only hold 2 electrons. So that is the octet rule. So we get to Lewis dot structures, which is what we're dealing with our electrons. Here's my first example. And I'm going to have this on the side eventually. You'll always know if you're doing it right because here's a check. Valence electrons, do I have the right number? I'll show you how to do that in a second. And then octets. Do I have everything has an octet except H? Then I'm doing it right. So I move down. Here we go. Cl2. We're going to go slow. Now we'll go bigger very quickly here. So here's my first check. How many valence electrons should Cl2 have? Well, chlorine, if you look in previous problem, has 7 valence electrons, right? 7. So there's 2 of them. So 7 electrons times 2. I should have 14 electrons. Well, unfortunately, if you bond a Cl with another Cl and give it each an octet, it'll have 8 each. That equals 16. Well, I can only have 14 electrons. So here's how we go. 1, 2, 3, 4, 5, 6, 7. There's 7 of them right there, okay? So I want you to understand that when we're trying to make bonds, so a bond, you're going to notice, usually incorporates 2 electrons. So this is called an electron pair. Whenever you have a pair, it's called an electron pair or a lone pair. When it's not bonded, this is a bonded pair. This is a lone pair. And I have 7 here. And then the more we do this, you'll understand that you want to have that extra electron pointing towards the other atom that you want, because that's the only ones that are going to bond are the single electrons. So again, I have 2, 4, 6, 7. So then I can circle this in my mind or on the paper but I want to clean it up. So ultimately, this is where the structure will look like. I have Cl, I have my bond, I change my electrons to a bond, and then I have Cl again. Here's my checks now. Do I have 14 valence electrons? Yes. And I can count them again. 2, 4, 6, 8, because it counts as 2, 10, 12, 14. Do I have octets? This is the trick. Anything touching an atom counts towards that one. Even if it's touching two different atoms, they're sharing. So this is 2, 4, 6, 8, because it's touching. I come over here, 2, 4, 6, 8. I get to count that again. So they both have octets, and I have 14, so I have to be right. So that's done. That one's done. What about this one? I know you can already see it, but here's a big key. I want a center atom. A lot of times there's a center atom. Unless there's only two, there's usually a center atom. So you have to figure that out. On that help sheet that's online under reference documents on my website, it gives you some rules. And one of the center rules of the center atom is the atoms that have the least, usually, except for H, the least number of valence electrons. Reason? It can grab onto more things. So first, CH3NH2. I did this one on purpose because it shows you a bunch of things. First, it's written this way. Why aren't the H's combined? Could be H5. It's not. So it's giving you a hint that the C has H's bonded to it and the N has H's bonded to it. So I'm going to count them all up. This is a coincidence that it's 14 again. The reason why it's 14, carbon has 4. Carbon is above silicon, so it's 1, 2, 3, 4. So it has 4. It's all in the same group. All these in the same group. So all group 1 has 1. Group 2 has 2. Group 13, 3, 4, 5, 6, 7. All noble gases have 8. Sorry. So this is 4. Hydrogens have 1 times 3. Nitrogens 5. Hydrogens 1 times 2. Add them all up, it's 14. So, and I put this out. So it makes sense to me that the carbon, the way it's written, has 3 H's bonded to it. So if you can see the red, because I kind of changed this, ultimately you won't be putting dots. You'll be doing lines more. But 4 dots, 1, 2, 3, 4. And then I put the H's around it, 1, 2, 3. I just bond them. H's can only have one bond, duet rule. Then I put the N, bond it, and N's have 5. 1, 2, 3, 4, 5. And then I put the 2 H's, boom, boom, and I'm done. Am I right? Well, I should have 14. 2, 4, 6, 8, 10, 12, 14. Do I have octets besides H's? H's just have one line. Good, 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 good. C, 2, 4, 6, 8. N, 2, 4, 6, 8. Octet. I have to be right. So then I did some extra problems that are on your worksheet for Lewis Structures 1. So for example, number 3, PCl3. The one that is outnumbered has to be my center atom. Has to be my center atom. So P is going to be my center atom. So I'm going to put that out there, 2, 3, 4, 5. And then I'm going to put my Cl's around it in space. I'm going to try to surround it. I don't care really about the shape completely, but I'm going to surround it. So I put Cl, and then it has 7, 2, 4, 6, 7. So hey, there's an extra one there, next one there. Bond, bond, bond. If you add these up, P has 5. Chlorine has 7 times 3, so you add that up, that equals 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I may have miscounted that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So they'd have octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So yes, I have to be right. There's one more thing called a dipole, and this is on that help sheet. And I'm just labeling it, that a dipole shows where the electrons are moving. And we use this as a tool. So the arrow points towards the negative and away from the positive. So I look at my electronegativity values from our first page. And chlorine is 3.0 and phosphorus is 2.1. So a difference of 0.9. It is not negative 0.9. It doesn't matter who's on the left or right. It's how hard it pulls. So it's pulling a difference of 0.9. So that's polar covalent. So what then I do is I make a little bond. Shoot, it's kind of stuck on there. You can put a bond dipole any which way you want. A little one above it on the worksheet, or all the way through. But what I'm trying to show is where the electrons are going. The chlorine with the larger number is pulling harder than the P. So the electrons are going in this direction. So I draw a dipole like that. Final one. Be very mindful on number 7. Number 7, boron is the middle. Boron only has 3 electrons. If you're looking at a periodic table, it's the group 13, so it only has 3. It's above aluminum, 1, 2, 3. So if I'm putting, I'm doing this on the fly here, if I put Cl's there, and I move them into position, I know Cl has 7. If it has 7, then it's 1, 2, 3, 4, 5, 6, 7. I want to put that single electron towards the middle. So what you're going to notice is that boron, see, I'm going to connect that one. I'm going to connect this one. I can circle it, but I'm going to connect it. Boron doesn't make an octet. So B and Al, whoa, are also exceptions. They can only have 3. Those are exceptions. They cannot make 8, but it's the best they can do. So that is the introduction to Lewis structures. It gets more complicated. It's called TV. I will try to get that to you as soon as I possibly can. That helps you with multiple bonds, but I'll just give you an introduction of just how you would do a multiple bond on this next page here. If I have O, I'm doing this on the mouse, so bear with me. If I have O2, I have oxygen, and I have oxygen, okay? And of course, it's not going to do that. And oxygen has 6. So what you do is, oh, I'm going to bond that once. And if I do, what it would look like is this. Again, they have 6, so that should be 12 electrons total, 12 valence electrons. So 2, 4, 6, 8, 10, 12. Good. I had the right valence electrons, but I don't have octets. 2, 4, 6, 7. Shoot, 2, 4, 6, 7. I don't have octets. So if you don't have enough electrons, you need to share more. So it needs to share more. So this is called a double bond. And now let me show you what that does. So that's 12, 2, 4, 6, 8, 10, 12. Each line counts as 2. And then do I have octets on each? 2, 4, 6, 8, 2, 4, 6, 8. So there are, those are my 2 checks to know that I'm right. So that's kind of where we're heading with that. So if you have any questions, please shoot me some emails and I will try to get you TV later, either tonight or tomorrow.